All right, I will get started with the introductory portion of our webinar today. This is a GCE Live Ask the Experts webinar, which means we have a panel of wonderful experts here today. They will be discussing your questions. You can enter those live and participate in this webinar actively by contributing questions for our panel. The topic we will be discussing today is water in mining, the application and use of models. And this is a 1 hour long webinar that will go from 1 p.m. Arizona time until 2 p.m. This is put on by the Geotechnical Center of Excellence. We are within the University of Arizona School of Mining and Mineral Resources, and we are an industry-funded, member-led interdisciplinary center, and we focus on a collaborative, practical approach to both geotechnical research and education, with the goal of bridging gaps between academia, industry, and fields of study. If you'd like to learn more about the GCE or our membership tiers, you can send us an email at gce@arizona.edu. And as I mentioned, we are member-led and member-funded. So on your screen here, you see a list of all of our member companies, and we want to make sure to acknowledge them because without them, everything we do at the GCE would not be possible. So thank you very much to all of our supporting members. We really appreciate you. And yes. And today's topic on water and mining is associated with one of our professional development courses, which is the Water in Mine Operations and Slope Stability course. This is an online course open to the public, and it is on demand, open for a year, self-paced with video modules that are viewable through an online portal. It is currently available for registration. You can either scan the QR code here, or you can go to our website, mining.arizona.edu/GCE. We cover a large range of topics within the realm of water in mining. So it's a great course. We've been running it for 5 years now, and it is one of our most popular courses. So I encourage you to check it out. And the course was underwritten by the Large Open Pit Project. And the content within the course is based on the Large Open Pit Project textbook called Guidelines for Evaluating Water and Pit Slope Stability with authors Jeff Beal and John Reed in 2013. If you'd like to know more about the LOP project, they do have a series of books. This is amongst a series that you can go check out at lopproject.com. And now we'll introduce the team here today and our panel. So from the GCE, the webinar team is myself. I'm Jillian Noonan, Senior R&D Engineer with the GCE, and I'll be your moderator today. And then assisting me from the GCE team, I have Benjamin Meyer, who's a software engineer for research and development. Thanks, Benjamin, for helping out today.
Hi, everyone. Thank you for joining us today.
And Cheryl Bukowski, who is our professional development program lead. Hello, Cheryl.
Hello, everyone. Thanks for being here.
And Greatness Ojum, who is a graduate research assistant working for the GCE for, I think, 5 years now. Greatness, thanks for helping out.
Hello, everyone. Thank you for joining us today.
And now it is my pleasure to introduce our panel. We have quite an amazing panel today. And starting off with Jeff Beal. Jeff is one of the authors of the book that I mentioned, the Evaluating Water and Pit Slope Stability. He's also a primary presenter in the Water and Mine Operations and Slope Stability course, as well as many of our other GCE courses. He also is Global Technical Advisor for Pitot Associates. Jeff, thanks for being here.
Hi, guys. I hope you enjoy the session. Nice to be here with you guys.
And then we also have Jeremy Dowling. Jeremy is also a primary presenter in the Water and Mine Operations and Slope Stability course, as well as hydrogeology advisor and president of Pitot Associates. Jeremy, we're really glad to have you on our panel today.
Yeah, hi everyone. Nice to be here.
We're also fortunate to have Jim Weigel, who is principal hydrogeologist with Rio Tinto Kennecott in Utah. Jim, great to see you. Thanks for joining.
Yeah, thank you, and looking forward to all the great questions I'm sure everybody has.
And we are joined by Blair Douglas. Blair is Global Practice Lead for Hydrogeology and Water Management with BHP. Blair, thank you so much. We're glad to have you on our panel.
Yeah, thank you. Hello all.
We have Travis White on our panel today. Travis is Principal Hydrogeologist with Anglo American, joining us from South Africa. Travis, great to have you.
Thanks very much, Jill. Hi, everyone. Great to be here again.
Yes, Travis is also a presenter, and Blair is a presenter in the course as well, I forgot to mention. And we have Ian Callow. Ian is Principal Hydrogeologist with Rio Tinto in Australia. Ian, thank you so much for being here.
Yeah, thanks, Jill. Hi, everyone. Really glad to be here.
Christian Sintalese, who is Lead Water for the Americas with Anglo American, joining us from Chile. Christian, great to have you here. Nice to see you.
Thanks, Jill, and welcome everybody to the session.
And Gus Rowland, who is Principal Hydrogeologist and Country Manager for South Africa with Pateau Associates. Gus, thank you and good to see you.
Thanks for having me. Welcome,
there you
everyone.
And next up, we have Michael Carroll. Michael is a Principal Hydrogeologist and Engineer, and Michael contributed a case study to the 2025 session of the course on water management practices in the Pilbara. He's with Fortescue Metals Group. Michael, thank you for being here.
Yeah, good morning. Thanks for having me.
And last but definitely not least, we have Pat Jenks. Pat is the Manager for Geotechnical Engineering with Nevada Gold Mines. Pat, thank you for joining our panel.
Thanks, Jill. Welcome, everyone.
All right, so that is our panel. They have a lot of expertise, and I hope that you have questions for them today. If you have a question, I'm going to let you know how you can submit that. So we have on your Zoom panel, there is a button that looks like the one you see here. It says Q&A. If you click on that button, a window will pop up where you can type in a question on the topic of water and mining, the application and use of models. You can submit questions anytime throughout the webinar. You can select a little button that will make your questions be submitted anonymously, and everyone can view the questions. If you see one that you like, you can vote for it with a thumbs up, and if there are highly rated questions, we'll make sure to move them up in the queue. We are recording this webinar, which we will post to both the watercourse site and to the YouTube page for later viewing. And just a quick note that the content in this webinar is intended for educational purposes only. And if you need site-specific professional advice, we definitely suggest that you seek out that also externally. Okay, so now we will get started with our questions. So we have some pre-submitted questions, but at this point, I would welcome our participants to go ahead and you can start entering in your questions through the Q&A. So we'll start off here with our first question pre-submitted. It is directed to the panel, so I will look for a volunteer to start off with this question. And the question is, when considering where to place targeted dewatering and depressurization efforts, is modeling an effective tool? If yes, what are the most critical data sets to collect and incorporate? So, panel, is there anyone that feels inclined to start off with this discussion?
This has got to be a Jeremy question, I'm thinking.
Yeah, go on. I'll just say a few words. I'll just kick it off. So, I mean, it's obviously a very case-specific question, right? Every site is different. But in most bedrock or deposit settings, most of the groundwater flow and occurrence is within the major structures or discrete fracture sets that are preferentially more conductive than the general rock mass. And so if you usually need to, for at least for general dewatering purposes, to remove water volume from the mine and lower groundwater levels, you usually need to place the dewatering pumping wells into those discrete fractures. And like I say, they're often controlled by the major faults. So if you have a good understanding of the structural framework of the site and the hydraulic properties of those structures and the hydraulic properties of some of the major fracture sets. You can put that information into the model, and then you can start to get some reasonable level of reliability about where to place dewatering assets and how they'll perform within the open pit when they're operated. If you don't have that information, and you just have a kind of general understanding of the site geology, then the model can quite often be very minimally useful in helping with the site or the location specific placement of dewatering assets.
Yeah, I mean, I think to add to that, I think general locations, broad locations, yes. Specific locations, no. As Jeremy says, if you're going to get decent productive wells, particularly in fractured rock, you're going to know where the fractures are, and there's no substitute for drilling pilot holes to get that. So the most critical data sets are really some pilot holes.
Yeah. Yeah, you need a really well-developed data set for the site in order to make the model reliable for those purposes. If it's a greenfield site or a site where there's not a lot of dewatering experience, it's very difficult to get that level of precision out of a model.
Well, I mean, from my perspective, it really comes back to the conceptualization, right? Which I know Jeremy and Jeff are very keen on. But without that conceptual model, it's really it's a bit blind. And so the data sets in my mind is very much the structural, the structural model, and any monitoring wells, piezometers you have around that, and their responses will dictate just how effective your depressurization efforts are and where to target next.
Of course, if you have a very uniform granular aquifer in the top of the pit slope that's feeding recharge into the pit, then that's a different situation, right? But it's different hydrogeology. It's a lot more uniform quite often, and so then you can use the model in a more generalized way. So it is case specific, but generally you need a very evolved data set and a lot of site experience to be able to get reliability from a model in terms of site specific location of wells or drains.
Yeah, I mean, I think you see a lot of operations which do try to use a general model to site specific dewatering wells, and very often the results aren't good. So you do need the site specific information. And if you're in a porous media and it's a dewatering well, you try and target the areas of greatest saturated thickness. If you're in fractured rock, you've got to go and pre-drill the fractures. And remember, it's not just a question of hitting fractures. You got to hit the deeper you hit them, the more sustained the yield of the well. So the answer to the question, I think, is generally yes, specifically no.
Yeah.
I might jump in and sort of add. Apologies, I just jump in and add some experience from one of our operations where it's a high flow, large permeability, porous media type example that Jeff was mentioning. And even in those situations, I think that the targeted aspect of the question probably still doesn't really apply. However, we utilize modeling quite effectively to assist with optimizing spacing of dewatering wells. So you might still utilize site-specific data from densely spaced drilling operations to try and cite your greatest saturated thickness, but you would utilize the model to sort of develop your strategy and where to place the wells. And I wanted to touch on the second part of the question as well, and just highlight the importance of collecting data from stratigraphic units that you aren't targeting. So I think we often overemphasize monitoring within our target aquifer system, but don't forget what's surrounding you as well.
I was just going to add to
Oh, go ahead, Blair, and then Travis.
Yeah, sorry. Look, I was just going to add, it's when not to use them as well, and knowing when to apply them, when not to apply them. I think that when you have strong dual porosities or very fractured flow, anisotropic flow, and a large portion of the rock mass doesn't have or contributing to dewatering, then sometimes that can be quite difficult to apply a model and get any sense out of it. So if you've got strong anisotropy with groundwater flowing only through fractures and large rock masses in between, the model will be misleading.
Yep.
Yeah, just to add, a very important point to perhaps make is don't bet your salary on your model, right? A model is just a tool in your toolbox. And Jeff, you agree? We're definitely very much aligned on this point. Models can be useful when applied correctly and within the correct context, but it needs to be used in conjunction with the rest of your tools as a hydrogeologist. Models, while they can be effective, they can also be value destructive. So it's very important to understand what your model says and when you're applying it and what your modeling objective was when that model was built as well.
All right, Jim.
Yeah, just to kind of echo a bunch of what everybody else has said. One thought that I did have that's slightly different is, if your model is indicating that there is a need for depressurization there, then it might be worth going out and doing some investigative work just to confirm that your conceptual site model is lining up with the numerics, and that if you were to put a depressurization effect, either a well or vertical drains or horizontal drains, that you actually have some water to pull out. Either way, that putting in that monitoring system is a needed piece of equipment, even if you were going to go and do some depressurization, because you need to basically be able to tell how much depressurization you're achieving. It can also be then used to figure out if you need to put in additional depressurization. And it helps you really cement down your conceptual site model and give you insight into how well your existing groundwater model might be predicting the current system. So, don't be afraid just because the model says there's something there or doesn't say there's something there, to go ahead and put in some sort of monitoring in those places where you might not feel like you have adequate characterization.
100%, Jim. That's such a good point. And I think it really reinforces the fact that your model is not a static tool, right? It's got to be developed and calibrated and validated over time as your conceptualization of the site develops and as you get more data. And running pilots and doing tests that can confirm that your model is adequately and accurately representing your site are really important. It's easy to get carried away by trusting the model without making sure that the model is really reflecting what happens in the real world.
Yeah, there's also a scale aspect, right? We need to think about. Right? So if you look at sort of the EPM, you sort of take the helicopter view, everything merges together in your model. Yeah, reflects everything beautifully as you get closer and closer to the, go back to the targeted question, right? Yeah, at a well spacing level or well diameter level, your scale is certainly much smaller than an EPM looking model. So in that regard, your model becomes less effective the closer you get to the area of interest.
So I think, Ian, you just started hitting on one of the follow-up questions we have that came in from the live group. But I will ask, is there any additional comments here?
Yeah, I will add one, that the models are also useful to quantify the level of effort, especially for budgeting on a 5-year cycle, typically, or 3-year cycle, and also to quantify the level of effort for the life of mine for dewatering. But I fully agree, when you go to specifics, then the modeling is just a guide, and you need to focus on any data that can enhance the conceptual model, typically piezometers or permeability information collected with RC drilling or any type of hydraulic testing.
Yeah, you know what, I just echo what Jim said earlier and advocate for the performance-based approach. Don't jump right into the model. Let's get some monitoring and some performance tools out there to assess how a test well or a test pumping well is going to perform. We've had a couple of cases in some of our operations recently where people have jumped right into the model, made commitments about performance, and they haven't come true because we didn't have actual good performance data to support the modeling work. So don't get too far out over your skis. Let's invest a little money and do some performance monitoring to support what we're proposing to do.
All right, thanks, Pat. I'm just going to pull up the question that we got from one of our live participants, and maybe Ian, I will call on you to just touch on this since you started talking about the topic of maybe like a representative elementary volume for the representation of EPM versus fractures. But I'll read the question out for everyone. Further to the first question, how well suited is the equivalent porous medium software, for example, ModFlow, FeeFlow, generally used in industry for what is more often than not fracture flow? Should we be using more DFN, discrete fracture network type software? And that came in from Zahn. I'm sorry if I said your name wrong. So Ian, did you want to go ahead and talk about that?
Thanks, Jill. Yeah, so the scale aspect to me has always been something that I'll be interested in. So as I said before, if you look at the helicopter view and you have your model that's kilometers by kilometers, you can site your wells perfectly and everything looks fantastic from a dewatering perspective or a depressurization perspective or any sort of modeling. But from a targeted point of view, as you get closer and closer, your REV changes, and then it really, in my mind, comes back to your site knowledge of your targeted zone, and the model becomes less and less useful for sort of local scale assessment. I've never been a huge fan of DFN modeling. It's a bit hocus pocus for me, and would much prefer to sort of stay focused on structural models and physical data, monitoring, that sort of stuff.
Yeah. So I'm gonna answer that a bit more directly. In
what does DFN stand for, Jeff?
In the real world, you should never use anything else but a EPM. You can populate the EPM with discrete features and boundaries and so on, but there is never a practical application in what we do to use a fracture flow model. And as you get further into the course, if you look at a DFN, every fracture is different. DFNs may be okay for general geotechnical anisotropy, but I've been involved with them a lot, and they just become misleading for hydrogeology because every fracture is different. And it's not, if you've seen the course, it's the pinch point of the fracture that is important, and you can never characterize that with a DFM. So the answer to your question is no.
Yeah, I completely agree with that. You'd have to understand the hydraulics of all the fractures in order to make it useful, and you can't possibly do that. So, it's all right to understand the fractures themselves, but then you need to understand whether they're, if they're full of mineralization or full of, calcite or clay, or they're just mechanically closed or discontinuous, then none of that helps with groundwater flow and movement. So there's a huge amount of additional information you need to know about the fracture networks to understand the hydraulics of those fractures that you just, there's too much information that you can't gather and put into the model at a scale that would help you, as Ian was saying. Whereas with an EPM model, in fact, although the underlying physics is equivalent porous media, you can actually put a lot of discrete features. If you've got a good structural model, you can put all the structures into the EPM framework and you can parameterize those. If you know something about the faults, you can include bedding geometries, and you can include the ore deposit and the intrusive geometries and the contrasting hydraulic properties of those different units if you know them. So you can create a very variable kind of the equivalent of a fractured media to the level of to the extent at which you have knowledge of that system within an EPM framework almost every time.
I might just add that there is a use for them though, isn't there? Where the geotechnical analysis shows there's a strong correlation between a failure mechanism which is driven by a specific fault, which is detailed and mapped, and it may have specific properties relating to clay content and water content, whether it's saturated or unsaturated. And I think they're the sort of areas, if it's useful to look at how hydrogeology and groundwater behaves along those particular structures of significance. And if they're aligning to geotechnical models, I'm not suggesting doing coupled models, but there is the opportunity there to test them if you need to see how they may perform. So it's back to what I think, Ian, you spoke about scale and getting down to that right level of scale. But it does also depend on what you're trying to achieve and what the geotechnical need from the model need to determine. Because if the geotechnical model's trying to, just say there's an error of, sensitivity to pressures of 50 meters, and your numerical groundwater model has an error of over that, it's essentially useless. So if you find yourself in that situation, you have to think of other ways to represent the groundwater system and still be useful in analysing the performance of it. I think all the discussion on making sure we get field observational data to demonstrate that the system is performing in a certain way, but we may also need to test locally.
All right. Any other comments here for Zan? All right, thank you to our panel, and believe it or not, we're already halfway through the webinar, so we do have a couple more live questions in the queue that I will pull up the next one, and I would welcome our live participants to enter those sooner than later to get a better chance of getting those brought up in this webinar. So the next question, I think maybe Blair, I will keep you on the line for this one from your high-level perspective with BHP. From your perspective, what aspects of hydrogeological information and water management have the greatest impact on the rest of the mining value chain? And that was an anonymous attendee, but thank you for the question. Blair, would you like to start with this one?
Yeah, sure. It'll depend on context, but whatever, in my perspective, would be whatever enables the mine plan to effectively be delivered in the most efficient way. So it's making sure you don't deviate from the mine plan, and water plays a role as an enabling factor. And the hydrogeological elements of that will depend on what you're trying to achieve. So if it's a pit floor, making sure you get your hydrogeology right so you can maintain water levels below the blast depths and allow them to progress. And if it's depressurization or flood mitigation, you're trying to get your pressures back behind the wall and stop water coming into the pit and diverting it. So it'll really depend on the context. So the three elements of dewatering, depressurization, and inflow management are the key things to maintain your pit function in a way that can achieve your mine plan.
Thanks, Blair. I see Travis, you had your hand up.
Yeah, thanks, Joel. Actually, a really good question. And I don't think there's a right or wrong answer, or more right or more wrong. But one thing I would definitely say, based on my experience, is get your baseline right. So get your data early, piggyback on your geotechnical and your resource geology programs, do the geophysics, try and expedite your groundwater and your water management programs. You know, don't wait till pre-feasibility B or feasibility before you get the work done. What we've started doing is, you know, bringing all your hydrogeological fieldwork campaigns one stage gate earlier, and that's paying real dividends in terms of down the line cost savings, risk mitigation, and ensuring that you got enough time to get everything you need to get in place. One big thing that's going to become increasingly more relevant globally are the permitting constraints. So ensuring that you have a good quality baseline information available, that can make your permitting a lot easier as well.
And then one thing to build on what Blair was saying, I mean, for geotechnical analysis, to support geotechnical analysis, it's really important that we focus the hydrogeological information on the defined zones of deformation or the critical failure surfaces. And too often we put in our piezometers too deep to be of value to the geotechnical model, where more often than not the failures are relatively shallow. So many mine sites I go to, I tell them not to drill the piezometers so deep, and I've just written a couple of reports today to that effect. So make sure you focus your hydrogeological information on the known failure mechanism or area of deformation.
Go
Might
ahead,
just jump in as
Pat.
well again.
Sorry,
Oh,
I'm
sorry,
gonna slot Pat in there. He's got his hand up.
Of course.
Yeah, thanks, Jill. Yeah, I have three things, and Travis alluded to it. Time is a key component of this. We have to be able to get out in front of this to be successful in order to meet that mine plan. So in order to do that, we need to be able to educate our leadership and inform them why it's important. Why do we need to be spending these funds now, so far ahead? You know, Travis suggested the stage gate ahead, and having the backbone to stand up for this. You know, we have a couple of projects currently where we haven't done this, and largely it stemmed from some people not being open-minded. You know, oh, we can't dewater that unit, so we won't be successful. Well, no one ever tried. So time, education, and really be open-minded and have that backbone to stand up for the need.
Yeah, I think one of the most frequent impacts, serious financial impacts you see in open pits due to water is just delayed ore delivery because of excess water, because the dewatering program hasn't been implemented in time. And actually, that's one area where groundwater models can be quite useful. They may not be actually giving very specific reliability about where to put the dewatering wells and drains, but they can give a general understanding of how much time you need to lower the water table or create depressurization to support the mine plan. And that's really useful information to show management and get support for the in-time dewatering program.
Probably going to just jump in and probably emphasize what I didn't catch the name of the first panelist, but what they mentioned around the permitting side of things. I think don't underestimate the potential scope of your influence on a mining operation as a hydrogeologist. You may commence your career thinking that your job is to lower water table on a particular bore on a particular day or for a particular 3-month plan. And then some years down the track, you find yourself in stakeholder engagement situations, informing upper management, like what was mentioned before, and really fighting for the importance of water management at the highest level, similar to what Blair would be dealing with. So look, I think the answer is everything in my perspective, and you'd be surprised how broad your reach could be depending on what your role is.
Yeah, that's a really good point, Michael. I think the concentrating on just the hydrogeological aspect kind of misses a part of the fact that water touches every part of the mining value chain, right? And there's no such thing as just a water department in a mine. There's a water aspect to every department on a mine. And so understanding how water behaves and moves through that mining value chain and impacts all the aspects of that mining chain are really important. And so you're always going to get your best bang for your buck where you understand your pain points and how water is affecting you.
Go ahead, Ian.
Yeah. Thanks, Jill. Blair, right at the start, mentioned context, which is to me the critical thing. Within Rio, we have a water risk framework which sort of speaks very nicely to this. And in that area, we break our water risks down into 4 buckets. And there's a deliberate use of the word buckets, but water resources, water supply, water resources, which covers water supply and stakeholder engagement, and well operation. Water quality and quantity, which covers our discharge requirements and what's our site sort of water balance, the ability to actually physically manage water on site, the dewater, depressurization, but also which hasn't really been discussed yet, is the long-term water management obligation. So how do our water management activities through operations impact our closure liability? And so we have a very nice framework that we can break just about every water risk we have on every site into one of those 4 buckets. Works really well.
Thanks, Ian. It's a good question. Any final comments before we move on to another? You've all given great advice. All right. Thank you so much, panel. And thank you for the question. I'm going to pull up another that came in from our live participants. And I am not really sure, this is with regards to underground mining and discrepancies in modeling with observed versus modeled. I'm not sure of our panel who has experience in this realm, so I'll just ask for a volunteer to start with this. I see Travis already raised his hand, but I'll read it out first and then we'll have Travis start. So this came in from our live participants anonymously. In the context of underground operations, have you encountered situations where modeling results contradict field observations? How do you manage the uncertainty associated with inflow predictions in such cases? And what recommendations are considered valid for addressing these discrepancies? So Travis, thank you for volunteering to start.
Yeah, this is exactly why you should never just trust the model. You should look at everything holistically. Yes, happened to me before and happened many times. Well, I'm sure to most people. How do you deal with it? Look, what we do as sort of a standard when we design the underground water handling capacity, we typically scale it up to 200% of the requirements. That's for a few reasons. Number one, in case your model's wrong and you haven't looked at everything else. Number two, water handling systems don't operate at 100% utilization or availability. So that's the redundancy that you build in there. A few other things you can do is whenever you do a modeling run, or when you're doing developing a new mine or sinking a new shaft, is to have continuous monitoring in place. It's pretty good practice to have piezometers around your vent shafts or vent raisers. If you're developing underground stopes or drives, get piezometers in your cover holes, or try and get and influence the mine design to have dedicated cubbies where you can drill holes from. I know that's easier said than done, but that is something that does work. And the good news is, where we've typically done this, we've saved a lot of money and reduced a lot of risk. So there's very few examples. In fact, I can't think of any really where the money spent on monitoring hasn't paid itself off, or additional monitoring. I'll leave it there. And Gus, I see you got your hand up.
Yeah, 100%. I couldn't have said that better. And one of the big challenges with understanding modeling results is what kind of a modeling result you've been given. Quite often, model results are given in terms of long-term average flows. And often it's the peak flows that are the real challenge in the underground operation. It's the sudden inflow from a structure that you hit unexpectedly with a cover hole, or a blast that goes into a structure that you weren't expecting. And so planning for peak flows is often more valuable and more important from a risk management perspective than planning for long-term average flows. And so making sure that your modeling team understands what question they're trying to answer is really important. And so often, as Travis mentioned, the characterization is so key. Understanding things like instantaneous yields and blow yields and expected average strike yield from things like cover holes is very important to make sure that you're sizing pumps adequately and sizing infrastructure adequately, that you're able to deal with rapid inflows of water if they might happen.
So one good thing about underground is you can do cross-hole testing and pumping testing without pumps, provided you've already got an operation. So, you know, again, several times this week, we've been encouraging operators to drill holes with a bit of collocation, shut them in, measure the pressure, and then drill holes, allow them to flow, and watching the response. So underground cross-hole testing is kind of fundamental to understanding how much water you might get and to how much your peak flows may be. And you know me, I'm going to turn that question around. I have never encountered any situation where modeling results don't contradict field observations.
Yeah, I think a lot of it just comes down to risk mitigation too, when underground mining is involved and you're using a groundwater model. The models that I've been involved with for underground, we usually intentionally overestimate the inflows just to make sure we have the pumping systems, the capacity, the power, everything in place in the event that we end up having, we come across those high flow units that Gus was referring to, so that you're able to manage it and not really disrupt operation. The worst case scenario is that you've gone in and you've undersized everything, and now you're waiting for procurement, which is, a year out, for getting pumps brought in or bringing in higher power systems so that you can feed the pumps, bringing in larger diameter piping so you can pull the water out of the underground facility. So for me, it's like a lot of the times, at least the ones I've been involved with, we intentionally overestimate the potential with the understanding that we are overestimating, but the hope and desire is that we are sized appropriately to reduce the amount of downtime at the operation.
Yeah, and I'll just back up Jim with that. There's also the education piece with mining engineers, who, in our experience, and my experience the same as Jim's in regard to this, and Dan O, who's on the call, is that the mining engineer's view is we just get a bigger pump, right? And they don't really understand, in many cases, the uncertainty that goes with hydrogeology, and our need to factor in that we don't have perfect knowledge, and the consequences, particularly underground, can be pretty catastrophic if you get it wrong.
Yeah, I mean, I've been involved with many flooded underground mines over the years, and more invariably, because you haven't drilled pilot holes or cover holes, sorry, ahead of the drift, or you haven't got dewatering holes into fractures. So, if you're going into new ground on a heading or a drift with no cover, then you're, depending on the situation, of course, you're potentially asking for unexpected inflows, which may give you a lot more inflow than you anticipated, and as Gus says, it's the peaks that you have to deal with.
Yeah, and this is where the conflict arises with minings, right? So every cover hole slows down production and development, right? And so it's really critical just to keep the risk forefront And a lot of times they don't understand it until they've experienced an unmanageable situation. They don't actually pay too much heed, which is a challenge.
Yeah, and that's such a thing, right? And it just highlights how important it is for hydrogeologists to work closely with geotech and geology to make sure that we're understanding the ground mass and characterizing what is coming ahead of us, but also how important it is to get water management and planning way up into the project planning stage. Too often we get introduced to a project when the mine's already been designed and built, and then they say, okay, how much water is it going to get? And that's not often the right question to be asking, is how do we deal with the water that we're going to get before we get it, and make sure that we're planning accordingly. And so making sure that water management is an integrated part of mine design before the mine gets dug in the ground is absolutely critical.
Can I just add that the question is asking about how you address some of the uncertainty. There are other techniques to do that. And if we take our potash operations, we've effectively used 3D seismic to look at cavities and areas which you can't actually represent in models. You don't know they exist until you've encountered them, and they have the unintended effect of flooding your operation and removing your ore body in this particular case because it's a salt. And therefore 3D seismic can penetrate down and define some of these cavities and features which could be quite problematic. So I think there's other techniques to reduce uncertainty. I think you've got the geology model. You can comb through that and start to try and look for correlations between rock type, structure, alteration, mineralization, and water to try and predict what it may be problematic as you penetrate through and use the geological basis to do that. And that obviously the modeling component of the underground is very problematic. And if you're talking about block caving or sublevel, you're inducing structure and stress into the formation and propagation of features which may penetrate vertically, which weren't there initially. And if you haven't got control and understanding how the mines behave through deformation, then you're probably going to struggle to represent and predict it. And therefore, that would be an enormous amount of the uncertainty and differential you get between observed and predicted.
Any other final comments on this question? All right, we have just about 10 minutes left in the webinar. I'm going to pull up another question. This one is addressed to the entire panel. So if you might each like to give your thoughts on this. I know Gus mentioned that it is very important for the hydrologist to interface with geotech, geology. But the question's asking, what are your best tips for collaboration between mine site hydrologists and geotechnical engineers in order to enhance the effectiveness of your modeling assessments? So I will first release this to Jim. He's got his hand up. Thanks, Jim.
Yeah, no problem. One of the best and most effective ways, I think, is to have your hydrogeologists and your geoengineers kind of embedded and working side by side, so they're both assessing the same plans, really working together, understand the system from geomechanics and a hydrologic standpoint. Otherwise, you have two different separate groups that are working separately. Maybe they think they're working towards the same same goal, but you don't really know. And ultimately, we're here to design open pit slopes, and the two components of hydro and the rock mechanics all kind of interact together and basically either produce stable slopes or produce unstable slopes. So I think the best way to get is just to make sure you're working very closely with your geotechnical engineers.
Yeah, and as I said earlier, understand for the hydros to understand the failure mechanisms and to focus their efforts on where the failure mechanisms may be and the zones of deformation and the critical surfaces, rather than rather than just putting instruments to often too deep. So just make sure you understand what you're dealing with in terms of what might fail, where the structures are, to make sure that the field instruments are focused on those, and both the hydro and the geotech. And one of the things we do a lot more of these days is put piezometers, TDRs, piezometers, shape arrays, piezometers, inclinometers, all in the same hole. So putting joint holes is a good way to get collaboration.
Yeah, Jim and Jeff are absolutely right there. Often the geotech and the geology team get much more budget for drilling holes in the ground than the hydro teams necessarily do. And so getting that integration and making sure that once you're buying a hole in the ground, you're getting as much information out of that hole as you possibly can. Making sure that you're extracting all of the value and don't grout holes before you put things like VWPs in them. So making sure that there's that interaction with the geology and the geotech teams as early as possible is really important.
And for everybody to understand the role of surface water, which is a major contributor in many unstable slopes.
100%. Yeah.
Yeah, just to add to that, and I think this is why this course is really great. Is we always try and pitch is that the hydrogeos need to know what the geotechs do, and the geotechs need to know what the hydrogeos do.
Totally.
So courses like this are really good. It's the easiest way to get a crash course on hydrogeology, and I would encourage all the hydrogeos that are doing this course to do the other more geotechnical specific courses as well. That'll really help you understand the full value chain, the full picture. And you shouldn't limit that to just geotech and hydrogeo. Learn a bit about engineering, understand how pumps work, even understand blasting. Blasting is one of the biggest drivers or mechanisms for water movement in an open pit and underground. So don't limit yourself and exploit courses like this.
Go ahead, Pat.
Yeah, just to add, one of the key things I would suggest is that learn from your geotech and geology counterparts what they are going to use from your work product, and vice versa. Learn what they ask them. What do you need from us to be successful? How can we help you be successful? As Jim said, embed with them, sit down with them, learn from one another. It's a team effort. One team, one mission. That's one of Barrick's sayings, and that really applies here. So take the time to learn how they use your work product. Take the time to learn how you can use their work product in better understanding hydrogeology and developing hydro models.
Yeah, and let's not forget that the only geotechnical parameter that we can actively vary and manage is pore pressure. And in terms of slope remediation and slope performance, depressurization is invariably the lowest cost and most effective option. So yeah, exactly.
We haven't heard from Blair, Ian, Christian, or Michael. Do any of you have any tips, Blair?
Yeah. So Jill, so
sorry,
sort of,
Ian?
yeah, thanks, Jill. So the embedding of the teams to me is a big thing, and across at least from our copper perspective, our hydros and geotechs work pretty closely together, and that includes our consultants as well. The other thing on my mind is that initial data collection, and take faults for example. From a hydro perspective, is a fault a barrier or a conduit, and it means slightly different things, for hydros versus geotechs, and so that initial collaboration at the field data collection period also is important. Yeah, and then that feeds obviously into the instrumentation of any drill holes.
Yeah, and another aspect that always enhance collaboration is having align the objectives of KPI between the teams. There's nothing worse than competing objectives between Hydros and Geotech. That's a way to make sure that there is alignment in terms of planning and an integrated approach, basically maximizing the value of every single hole drilled on the mine.
Sorry, Christian. I think the one thing to add to the discussion is make sure you align your data sets to the type sections of geotechnical analysis.
Yeah.
You've got if the geotechnical analysis are in 2D sections, make sure you study those sections and you understand them, and that you understand as a hydrogeologist and vice versa, what's the sensitivity of pressures in this area and what's the uncertainty of that sensitivity. So then you can actually structure your monitoring network to be within that range of detail, because there's no real point in having a very detailed hydrogeological section areas which don't matter, but also vice versa. If it's complex geotechnical analysis and you've got one vibrating wire, it's not enough. So being able to, like I said earlier, if your error in your hydrogeology is greater than your uncertainty, so your sensitivity to poor pressures, you've got to do some work. And that's the first thing I always look at is, what is that sensitivity? What is the failure mechanism? What do I know about the hydrogeology and how erroneous could it be, and how that then needs to be improved to get to a level of confidence? Geotechnical engineers will just run with the pressures that they use. They'll probably typically use a phreatic surface with a hydrostatic distribution. We know that's not the case. So one of the important things we need to do as hydros is educate geotechs around variability in pore pressure profiles and why it changes in a 2-dimensional or 3-dimensional system, and really work with that. And the second thing we really need to push them on is make sure they demonstrate the sensitivity of pore pressures, and that you work through depressurization effects to see what is required to bring it back in line with stability, and whether or not you can. And be realistic about it, and make sure you then set together trigger action responses, TARPs, which you both agree to based on the science that you have at the time.
So it might be worth mentioning as well, and then Blair, you sort of touched on it towards the end there, from the governance side of things. I think it does help in some situations, depending on your organization, to actually have some documentation about how geotechs and hydros are going to collaborate, whether it's a hydro pore pressure assessment guideline or some form of collaborative framework that can be useful.
All right, any last words from Jeremy or?
No, I think everybody's covered a lot there. I think the integration of all the different types of monitoring data is really key. So if you've got several different types of slope deformation data, be sure to integrate all the hydrogeologic data with that and interpret all the data sets together. So if there are piezometers near an area of deformation, then plot the piezometric data and also the climate data with the slope deformations, and try and understand how the pore pressures are affecting the deformation mechanism. And that can then be used to create an empirical calibration of the slope behavior and its sensitivity to pore pressure. So I think just having very integrated slope monitoring data is a really important way to integrate the hydro and the geotech to get more value out of both, and ensure it's all aligned in understanding the slope and how to manage it.
Thanks, Jeremy. Blair, I see you typing an answer to the question in the Q&A. Yeah. Okay, so
Yeah. Sure.
Nsako, your question, Blair is typing an answer there. I'll leave the webinar. Are you intending to finish it?
Yeah, it's complicated, that one, isn't it?
It is, yeah.
We've run out of time as well, I think.
Well, I won't rush you out. I can leave the webinar open so that you can finish typing that. But I do need to release the rest of the panel who may have things they have to go do. It is 2:01, so we're 1 minute over. That was a great session. I'm not surprised because we have such a great panel. We're really honored to have you all here today, supporting this effort that we're doing here, trying to get out, best practice information and to coordinate globally with everyone working within a similar industry that we all are invested in. So we really appreciate you guys being here. Very quickly, I'm just going to run a few things by you. So Travis mentioned the importance of understanding blasting and other geotechnical considerations that might deal with water. Just so we have a new course this year at the GCE, which is going to be released in September. That is blasting and pit slope performance. And we actually have on our panel, one of our lead technical advisors for that course is Pat Jenks. So it's going to be a great course. I think Pat agrees. And we hope to see you all in that course. I think in the chat also my assistants, I don't know what to call them, have posted a link to our website if you want to go see the rest of our courses that are offered. And the course that we are primarily focused on today is the Water and Mine Operations and Slope Stability course. So I will throw that up here and I will leave that up for a little while so that you can scan that code if you need to. And I will leave the webinar open. So Blair, if you wanted to finish typing the question for Nsako, then you could do that. But the rest of you, thank you so much. Really appreciate you being here on the panel today. And thank you so much to our participants. We will have another water webinar coming up. Cheryl, do you have that date on hand?
September 23rd.
September 23rd. So look on LinkedIn for that announcement and registration. And we hope to see you at that webinar. And many of our panelists here will likely return on that date as well. So thank you so much. And I hope you all have a great morning, evening, whatever time it is where you are.
All right, guys. Thanks for a good session.
Thank you.
Thanks, everyone.
Thank you very much, everyone.
Bye-bye.
Bye.